Right. So work power and energy. So quick recap of what we had learned last time. We had seen that work done denoted by W. Okay. So work done by a constant force F over a displacement of S is defined as, so it is Fs cos theta. Okay. Now before we proceed with the interpretation of this, let's also understand in this that it is a scalar quantity that comes from the scalar product of two vectors. Secondly, work done can be positive if theta is acute. Work done is zero if theta is equal to 90 degrees. Okay, and that is force is perpendicular to displacement. Okay. And work done can be negative if theta is greater than 90 degrees or obtuse angle. Okay. And the next thing, work done SI unit, joules, where 1 joule is equal to 1 Newton meter. CGS unit is erg, where 1 erg is equal to 1 dyne centimeter. So just make a quick note of these few things. Okay, and we had also seen that therefore 1 joule is 10 raised by 7 ergs. Okay, next let us understand a couple of ways to interpret the definition of work done. So if on a particle we are applying a force F like this, while the particle itself is making a displacement like this, let us say, where the angle between these two is theta. So we know the definition of work done is F dot S, which further reduces to Fs cos theta. Now this can be interpreted in two ways. Okay, one is that you can write this as F cos theta into S. So that in this diagram, just make a copy of this diagram because we have two interpretations. Yeah. So in this diagram, the first one, you can see that F cos theta kya hai? It is the projection of force along the displacement. This is your F cos theta. If we drop a perpendicular from the force vector onto the displacement, this is your F cos theta. Okay. So the interpretation of this is work done is the component of force along displacement multiplied by displacement. That is one way of interpreting it. Okay. The second way of interpreting the same thing is that you can say that this is force into S cos theta. Now S cos theta kya hai? So for that we have to understand that if this is the direction in which force is acting, and what we do is we drop a perpendicular from our displacement onto that direction. Then the component of displacement in the direction of force, that becomes this. So this is the interpretation of projection, or component of one vector along another. This is like that parallel component, like that. Okay. So it can be interpreted also as alternately work is force multiplied by component or projection of displacement along force. Okay. So these are the two ways in which we can interpret the work done quantity. And same way, when we are calculating work done from a given force, work done by a given force from a diagram kind of situation, then there are two ways in which we can do the calculation geometrically. We can either drop the perpendicular from force onto displacement, so that will give us the component of force along displacement and multiply that with the displacement, or we can do the reverse of that, that we can drop the component of displacement along force and multiply force with that parallel component of displacement. Okay, so just make a note of this. You can also think of this as the parallel component of force multiplied by displacement, or the force multiplied by parallel component of displacement. Okay, so hope this is clear. So let's look at an example problem. So we have a rough horizontal surface like this. Coefficient of friction is 0.2, and on this block we are now applying combination of two forces. So a block of mass m equal to 10 kg initially at rest. Now a combination of two constant forces such that F1's magnitude is equal to 200 newtons, and this angle alpha is 37 degrees. F2's magnitude is 250 newtons and beta is equal to 53 degrees. Starts acting on it. So calculate the work done by each of the forces acting on the body through a displacement of 20 meters. So just work this question out quickly. Okay, make the mass of the block 20 kgs, okay, and take the value of g as 10 meters per second square. Okay, anybody got the answers for this? So first of all, let's calculate all the forces. Okay. Other than F1 and F2, there are a number of forces acting on the body. So let's understand that first. So in total, what all forces are acting on it? There is weight of the body. Okay. There is F2, there is F1, there is normal reaction, and there is friction. These are all the forces which are acting. Okay. So when we break this into components, you can see that this will be F2 sine alpha. This one will be, sorry, I got the angles mixed up. This one is alpha, this one is beta. So what will be the values of these two? So F2 was 250 and beta was 53. So this component will become how much? 250 into sine 53. So that will be 200 newtons. And this component will be 150 newtons. 250 into cos 53. Cos 53 is cos 53 is 3 by 5. Now similarly, F1 will break into components. So this component will be F1 cos alpha. So that will become how much? 200 into 4 by 5. So that will be 160 newtons. Okay. And this component will be 200 into sine, sine 37. So that's 3 by 5. That will be 120 newtons. So this I have broken these two into components. Okay. Then of course the weight of the object we already know, that is 200 newtons, 20 kg. So how much does a normal reaction become now? So this becomes the important thing for us. What is the magnitude of the normal reaction? Because friction will depend on that. So from this diagram you can see normal reaction is equal to mg plus f1 sine alpha but minus f2 sine beta. So it is 200 plus 120 minus 200. So the normal reaction is 120 newtons. Okay. So that will tell me how much the kinetic friction is, because the object will be accelerating like this. So that kinetic friction will be mu n, and that will be equal to how much? Coefficient of friction was zero point 0.2, I think. Yes, yes, zero point 0.2. Okay. So kinetic friction will be 24 newtons. Okay. Now we are looking at a situation where the body is going to displace like this. The displacement vector of the body is going to be in this direction. So from this now you can calculate the work done by each of the forces. So calculate. Next thing, I want to calculate work done by F1, F2, normal reaction, weight, and friction. Each of these forces, how much work done is there, that you can understand now from the given data, right? So make a note up to here and just work out the final values. Okay, so hope it is clear up to this point. So let's work out each of these now. So you can see that displacement is horizontal. So we need to calculate. So this one, work done by F1 will be equal to F1 dot S. So that we can easily write as, because we already got F1 cos alpha into S. So इसको ऐसे directly लिख सकते हैं. It's quite easy. So work done by F1 is becoming how much? This 160 newtons multiplied with the displacement, which is 20 meters. So 3200 joules. Or you can also write this as 3.2 kilojoules. Okay. So Varun, your answers are correct. Work done by F2. Similarly, calculate F2 dot S. So that will become this component of F2 multiplied by the magnitude of displacement. So 150 newtons, one 150 newtons multiplied by 20 meters, or 3 kilojoules. Now work done by normal reaction, that will be zero, you can see, because normal reaction is perpendicular to displacement. Same goes for work done by gravity here. Because gravitational force is, I mean, the displacement is horizontal. So these two are zero. And the fifth and final one, work done by friction, that will become how much? So when you take dot product of kinetic friction with displacement, it is 180 degrees. So the minus of kinetic friction, which we saw is 24 newtons multiplied by 20 meters. So minus of 480 joules. That is the work done by the friction. So these are the work done by each of the five forces which are acting on the body. Yeah, Vani, the reason why minus sign is taken for friction, na? See, the displacement of the body, that is happening in which direction? The displacement is happening along the positive x-axis. Okay. Whereas the friction is acting in which direction? It is opposing the slipping. No? So friction is acting in the direction which is the negative x-axis. So what is the angle between the force and the displacement vector? It is 180 degrees. No? That's why the dot product gives you that cos 180 term. That's why. So work done by friction is this. So that cos 180 term is negative 1. So it is 24 newtons multiplied by 20 meters multiplied with minus 1. That's why. Yeah, सर्विस the direction of displacement will depend on the surface. ना यहाँ पे horizontal surface पे ऐसा push कर रहे हैं, so it will have a horizontal displacement. Last time we did a problem on an inclined plane. The body was sliding down the inclined plane, so the displacement's direction was along the inclined plane. So that really depends on your mechanical system. You understanding, beta? Yes. So kinetic friction will always do negative work. Okay. Static friction, on the other hand, can do positive work. I will show you situations like this. But wherever there is slipping, so the type of friction acting is kinetic friction. Okay. So kinetic friction always ends up doing negative work. So later we will see that that is why kinetic friction is called a dissipative force. It dissipates energy. When we understand the concept of mechanical energy for a system, we will see that kinetic friction is a type of force that always dissipates the mechanical energy. Because of kinetic friction, a system's mechanical energy tends to decrease with time. It tends to dissipate. But we'll talk about that a bit later when we discuss about work energy theorem. Before that, we need to understand a few more definitions. Okay. When we are driving a car, Sarvesh, unless we brake very heavily so the tires skid, the type of friction acting is not kinetic friction. If the tires are not skidding, the type of friction acting on the wheels is a static friction. In fact, it is called something called rolling friction because the tires are in a type of motion which is called rolling motion. Yeah, so for an accelerating car, the type of friction acting is not kinetic friction. It's a type of static friction, in fact, called rolling friction, and that does positive work. Okay, now next thing we'll see is a situation where we are dealing with a variable force. Okay, so if we have a situation where the force acting on a body is not constant, but it varies. If F is a force which varies in magnitude or direction or both through a displacement from some initial position, let's say Ri, to a final position, Rf. Okay. Then the work done by this force is calculated by a process called path integration. So let us understand what this process is. Okay, so imagine I have a situation where this is the initial position of a particle and it is being moved from this initial position via some path like this to this final position. So this is my initial position, my final position. Okay. So in proper vector algebra, we represent position, as you know, we represent it as a vector. We have learned this in kinematics. Okay. That with respect to your coordinate frame, the position of any point, how we write it in vector algebra, we write it as a vector joining the origin of the coordinate system with that point. So this is my initial position and this is my final position. Now, while the body is moving from here to here, if there is a force acting on it, which all the time varies. And so when the body is here, the force is like this. When the body is here, let's say the force is like this. When the body is here, let's say the force is like this. So you can see continuously the force's magnitude and direction both are changing because the length of the arrow that I'm drawing, that is also changing, and the direction in which it is pointing, that is also changing. So in such a case, how we will calculate the work done? We'll calculate the work done by a method called path integration. We just make a note of this diagram and this statement first, then I'll explain what is path integration. Okay, so what we do to calculate the work done in this path integration is that we take very small displacement at a time, like a ds over here, or a ds over here, or a ds over here. So instead of taking the whole displacement from initial to final position, okay, we calculate work done during what is called a differential displacement. Differential का मतलब क्या होता है? Very small. So that becomes a small amount of work done. So that is F dot ds, where F is the instantaneous because it is varying. So it is the force at that instant. So it's the instantaneous value of the force F during the differential displacement ds. Okay. So once we calculate this, the next thing, the total work done, net work done from initial position to the final position, that becomes integration of this. So from that we have the definition that work done becomes integration of F dot ds from whatever initial position, whatever final position. So this is in fact the general definition of work done. You can say that the definition F dot s is, it is a special case of this definition when what is happening when F is constant. So this is in fact the more general definition of work. That work is the path integration of force. So this might look very complicated in the diagram, but we'll break it into simpler cases and you'll understand easily. Okay, so hope you've written this down. So one thing we can understand that from the general definition itself of work, that is work is equal to integration f dot ds, initial to final, we can show that for a constant force, integration f dot ds becomes f dot integration ds, because the force is constant, so it can be brought outside the integration. So that becomes f dot s. So this is a special case of this formula, provided force is constant. Whereas for a variable force, work done has to be calculated by integration. So examples of variable force are, for example, spring force, F's magnitude is kx. There is electrostatic force between two charges. You know that electrostatic force is some constant into q1 q2 by r square, where r is the distance. So you can see the force is varying with position. Okay. So not all forces are going to be constant, like mg, normal reaction, friction, etc. in the examples we have taken. It is only certain forces in certain systems which are constant. But the majority of forces in nature and real life are variable forces. So for that we have to use the general definition of work done, that it is path integration. It's path integration of force over displacement. Whereas this is a simple scalar product. Okay, next up, let us look at an example of application of this integration formula. Okay, so a particle moving along the x-axis experiences a variable force given by this formula is along the x-axis, so I cap, where alpha is a constant equal to, let us say, 2 into 10 raised power 3 Newton meter square, and x is the position in meters. Okay. So calculate the work done by this force F as the particle moves from an initial position, let's say A, given by the coordinates 50, 0, 0 in meters, to a final position B, given by the coordinates 100, 0, 0 in meters. Okay. So just note down the question. I'll explain how to work it out. Okay. So if we visualize this problem, यहाँ पे क्या हो रहा है exactly? My body is moving along the x-axis. So first of all, it's easier because it's a one-dimensional problem. So let us say this is the point A, which is at x equal to 50. Let's call this x1. And this is the point B, which is at, let's call this x2 equal to 100. X is in meters. Now, while the body is moving in between, what is happening? The force acting on it is along the x-axis only, but it's a variable force. So जब यहाँ पर है, इस पे जो force लग रहा है उसका magnitude कितना है? The magnitude of that force is alpha by x square. Okay, where at this particular point P, let's say the x coordinate is some x, which is greater than 50 but less than 100. So when it makes a very small displacement over here, when it makes a differential displacement, that differential displacement is going to look like this. वो ऐसा displacement होगा dx. So in this particular case, you can see that we will use the formula f dot ds. Okay, this is work done by a variable force f, but in this we will substitute f as alpha by x square I cap in vector form, and the differential displacement, as you can see in the diagram, is having only one component, only the x component, because it's given to us that the body is moving along the x-axis. So using that, we can see that the displacement is like this. So f dot ds will become a very simple thing here actually. F dot ds should be just replaced with alpha by x square dx, because I cap dot I cap is 1, because you know this thing, I cap dot I cap is unity. Okay, so from there you can see that we will define the work done from initial to final position as alpha dx upon x square, where the initial point is A and the final point is B. So we will substitute the limits after taking the constant outside. So for the point A, x का वैल्यू कितना हो जाएगा 50 and for the point B, x का वैल्यू कितना हो जाएगा 100. So now we have to just carry out this integration. Okay. Now you know that the integration of dx by x square is x to the power minus 2. So that is x to the power minus 1 upon minus 1 plus c. So it is nothing but minus 1 by x. So the indefinite integration is like this. Okay. So the definite integration is like this. So that in fact becomes 1 by a minus 1 by b. Okay. So use this over here and work out the final answer, please. Yeah, because Rahil, see what is happening. The general definition of displacement in a XYZ system would be like this, ना? But यहाँ पे क्या हो रहा है? ये दोनों zero हैं. Why? Because the motion is along the x-axis only. Okay? It's moving along the x-axis. That is given to us in the question. Okay, which is why first of all I illustrated this point here. That because it is given to us that the body is moving along the x-axis. So in the diagram also you can see the same thing. That displacement का direction क्या है? A to B है ना directly. So it is only along the x-axis. So the ds vector has a magnitude of dx, small change in x coordinate. And what is its direction? It's I cap along the x-axis. Is it clear, I'll? Okay, good. So now just note down up to this step and put the limits and calculate the final answer. Alpha's value is also given to you above. It is 2 into 10 raised power 3 in Newton meter square. So put the limits and get the final answer with the proper unit. Now work done you should be getting in joules. Okay, so let's confirm the answer of this one. Okay, so all you have to do is substitute the values now here. So this becomes alpha into minus 1 by x from x equal to 50 to x equal to 100. So it becomes alpha whose value was 2 into 10 raised power minus 3, right? That was the value of alpha I had given you. So 2 into 10 raised power 3. So 2000 into 1 by 50 minus 1 by 100, which is 1 by 100. So you can see that is 20. Now the unit will be what? See, alpha is in Newton meter square and x is in meters. So the unit will become Newton meter square divided by meter. So that is Newton meter or joule. So that will be the unit of the work done. So it is in joules. So plus 20 joules. That is the correct answer for work done. नहीं बेटा राहिल, the integration I have explained to you on the side here na. See, the integration is dx by x square. See, that's why I gave you all these steps over here. We are integrating this quantity dx by x square, that is here. It is not integration of dx, it is integration of dx by x square. Have you understood now? तो बेटा ये स्टेप देखना यहाँ पे, what is the integration we are doing? The integration is this function ना. It is integration of dx by x square. It is not integration of dx. ऐसा थोड़ी है, ये नहीं है, ये है. You know the general formula now of integration. ये आपने सीखा है ना कैलकुलस में. So here it is what integration of this, that is integration of x to the power minus 2 dx. So that is minus 1 by x. Okay. Okay, let's move on to one very important example, or let's say formula of work done. That is work done by spring, work done by spring force. Okay. So earlier what we have learned about a spring is that when the spring is at the natural length position, then the spring force is zero, or you can say tension, which is the spring force, is zero. But the moment we want to stretch the spring, a restorative kind of tension develops. So this is what we call the spring force, and that is equal to kx. So that has to be balanced with some external force. Okay. So on stretching a spring by x, okay, what we call a restorative force, that is, it tries to restore itself, or a restorative tension develops. Similarly, if you want to compress a spring from its natural length to a compression of x, then this time an outward type of restorative force develops. That has to be countered with an external force acting like this. So on compressing a spring through x, again a restorative force or tension equal to kx in magnitude develops. Now what we want to do next is we want to calculate work done by this spring force. So you can see it's a variable force. It depends on x. So here the quantity k is called the spring constant, or also call this the stiffness of the spring. So k is expressed in newtons per meter. That is the SI unit. Okay, so let us understand work done by spring force. Okay, so our next example, we have this situation. We have this block attached to a spring of constant k and natural length L. So a block is attached to a spring of spring constant K, and what is called natural length, that is when the spring is not deformed, L, as shown. Okay. Now the block is slowly pulled to the right side through a displacement of x naught. Okay. So you want to find the work done by the spring force in the process. Okay. So from here, what we start doing is we start applying a force on the block in order to pull it from here to this kind of state. Okay. So we apply some kind of external force so that stretching like this, and eventually it reaches a position where it has been displaced through a net value of this. So this is the final position. This is the initial position it is starting from, and this is some intermediate position, that means in between. So the system is going from here to here, then from here to here finally. So very gradually, okay, very slowly we are making this change. In the process, we have to calculate the work done by the spring. So note down the question first, then we will understand. Okay, so let's understand the work done by the spring. So this spring force at this point of time you can see is like this. It is going to be kx but acting in the backward direction. Okay, and if we take this as our x equal to 0 position, in comparison to that, this is when the displacement is x. Okay, so we can see that we want to calculate work done by spring force, but the spring force is a variable force, okay, because its magnitude is kx and direction is minus I cap. Okay, so we can write the spring force here as minus kx I cap like this. So what we have to do is we have to calculate work done by integration of this spring force over displacement. Okay. So we look at this situation where this is L plus X and spring force is acting like this. And then from here, we look at very small further displacement. So this displacement from here to here is dx. Okay. So ds, as you can see, is again along the x-axis, along the spring. And the spring is what we're taking as the x-axis. So during that small thing, the work done by the spring is minus kx I cap dot product with dx I cap. Or very simply in the diagram, you can see that the work done by the spring will become minus of f dx because f is acting in this direction. See, f is acting in the direction opposite to the displacement dx. This angle is 180, so it is minus kx dx. Okay, so that way also you can understand that this is going to be integration of minus kx dx, but from where to where? From initial to final position. So initial position में x कितना था? 0 था, और final position में x का value कितना है? x naught है. Okay, so it is minus half kx naught square. Again, why that is the case here? Because when we do the integration, this step minus k comes outside, x dx going from x equal to 0 to x equal to x naught. So now integration of x dx is how much? It is x square by 2. And on that we'll put the limits 0 to x naught. So this will become minus k x naught square by 2 minus 0. So that's how it becomes minus half. So as you can see that when you stretch the spring is doing negative work, because the direction of the spring force is opposite to the direction of displacement. The spring force is acting like this, whereas the displacement is happening in this direction. So it does negative work, but the work done is given by this quantity. So for example, if the spring constant is, let's say, 20 Newton per centimeter, and we are stretching it by, let's say, 5 centimeters, then the work done by the spring will become minus half k. Now this will have to be converted. So it will be 20 into 10 raised power 2 newtons per meter. Which will have to be converted to become 5 into 10 raised power minus 2 meters. So this much in joules. So as you can see, that will become minus of 5 into 10 raised power minus 1 or minus 0.5. Okay, so just make a note of this quickly, please. No, there is no information about the external force. Okay, so we will come back to that later. Right. So obviously, if you are stretching the spring very slowly, the external force has to increase very slowly. No, you cannot apply a large amount of force straight away because then the block will accelerate. So the external force that we are applying is very slowly being increased. But here we are not concerned about that. Okay, we are concerned by the work done by the spring, and that is coming out to be minus half kx naught squared. Oh yeah, sorry, my mistake. This is squared. So this is, just make a correction here. This will be 25 into 10 raised by minus 1. That's correct. This is okay. Okay, so just make a correction here. Tika, that is correct what you said. But remember that there's a minus sign. Huh? Don't forget the minus sign. It's minus 2.5 joules. Okay, so hope this is clear. Now, the next thing we'll see is that as opposed to stretching the spring, suppose we are compressing the spring, then what kind of work the spring would be doing? Would it do negative work? Would it do positive work? Let's understand that. So if this is the initial position. Now an external agent slowly pushes the block leftwards until the compression of the spring is x naught. So calculate work done by the spring during this process. Okay. So we start pushing it like this now so that it reaches a final position where it has compressed to x naught. So this is the final position. This is the initial position. So again, if we look at some intermediate position where the compression had become x, so this is now L minus x. So what is the direction of the spring force? It is outwards. Okay. Here also, what is the direction of the spring force? It is outwards. But what is the direction of the displacement? Is going to be inwards. So at some intermediate time, you can see that spring force is acting in this direction. Its magnitude is kx, and the block is going to make a displacement in this direction of dx. So work done by the spring during that small displacement is minus kx dx. Okay. So total work done by the spring will again be minus kx dx integrated from, now this time we can take the x coordinate going from 0 to minus x naught also, it doesn't matter, okay, because it's a whole square term. So ultimately whether we have reversed the direction of the x-axis or we are using the same x-axis, it doesn't matter. But the work done by the spring will again come out to be minus half k x naught square. So what this tells us is something very important, that going from natural length position, if we deform the spring by x, that is we either extend it or compress it, the work done by the spring is negative. So if a spring initially at natural length position is either compressed or extended by x, the work done by the spring in both cases is minus half kx square. In both cases of whether x is a compression or an extension. So this is something very important to remember here. So in this particular case, I'm not worried about what the work done by the external agent is. Okay, we'll come to that later when we discuss about work energy theorem, etc. Okay, I'm just concerned that as the external agent is taking the system from the initial position to the final position, what is the work done by the spring force, or what is the work done by the spring? That comes out to be minus half kx square. Yes, we will do all that, Sarvesh, but that we'll do in the next stage when we discuss about work energy theorem. First, we have to learn the basic concept of what is the work done by the spring. So the important concept is that the work done by the spring is minus half kx square when we go from initial state of natural length to a final state of compression or extension by x. Okay, so from this we now develop a general formula for work done by a spring. It is minus of integration kx dx going from initial position to final position. Okay. Because so here x can be negative in the case of compression or positive in the case of extension. But the spring force is always opposite to x. Okay. So you can see that this is a natural length position. In the case of compression, here x is negative. So spring force is in which direction? Positive direction. So it is opposite x. If we go from here to a state of extension, so compared to this, Here x is positive. So spring force is in which direction? Negative direction. So it is opposite to x. When x is positive, spring force is negative. When x is negative, spring force is positive. So that is why we can in general write this is minus kx dx. Okay. So the general formula for the work done by the spring becomes minus half k into whatever final position square minus initial position square. This becomes the general formula for work done by the spring. Okay. So for example, if a spring of spring constant, let's say 10 Newton per centimeter, is taken from an initial state of compression of 1 centimeter to a final state of extension by 2 centimeters. Calculate the net work done by spring force. So we'll just use this formula. Work done by the spring force is, okay, so it is minus half k x initial square minus x final square. Now here we will substitute x initial as minus 1 centimeter or minus 1 into 10 raised power minus 2 meter because it is a compression. Whereas we will substitute x final as plus 2 centimeters or plus 2 into 10 raised power minus 2 meters because it is an extension. But as you can see, the term is whole squared, so the sign actually doesn't matter as far as the work done is concerned. So the net work done by the spring will become minus half into k, which is 10 into 10 raised power 2 Newton per meter into x initial square minus x final square. Okay. So finally, this term will become minus half into 10 raised power 3 into 1 minus 4 into 10 raised power minus 4. So as you can see, oh sorry, we have to do x final square minus x initial square. My mistake. So we've taken the minus sign outside. So this will become 2 into 10 raised power minus 2 whole square minus 1 into 10 raised power minus 1 whole square. This becomes 4 minus 1. So this will become minus 3 by 2 into 10 raised power minus 1. This is the work done by the spring. This particular case. Okay. So this is how we apply this general formula that work done by the spring in any process is minus half k x final square minus x initial square. So this is an important formula for us to remember. And we'll always use the sign convention that compression is negative x extension is positive x. Okay, so hope this is clear to all of you. So I'll be sending you a basic assignment now to do with the concepts we've learned so far in this week. And next week we will discuss about, the first thing we'll discuss about is the work kinetic energy theorem. And the second thing we'll discuss is potential energy. So you can start reading ahead about these two things. The relationship between work done and kinetic energy, which is called the work kinetic energy theorem. And the second thing will be the concept of potential energy for a system. So for example, we will see elastic potential energy of a spring. We will see gravitational potential energy, because of the gravitational field of Earth. So that's it for today, people.